Hello, everybody, and welcome to our webinar on XFdtd Schematic Editor. This webinar coincides with the recent release that we had with XF 7.11.0, where we introduced optimization in the schematic editor, system efficiency, and subcircuits. Instead of just having a what's new webinar focused on the latest release, we decided to do a full webinar dedicated to the schematic editor because there's a lot of features and capabilities and use cases that we wanted to make you aware of. And so I'm Jeff Barney. I'm the product manager for XFdtd, and also on the line with me is Sam Seidel. He's the project manager and manages the development team and the code base. So we are going to go ahead and cover this webinar today and this topic. There'll be a point where at the end we stop and have an opportunity for you to ask questions, and I can answer them live if I know what the answers are. But throughout the webinar, you're welcome to go ahead and open your GoToWebinar panel and enter questions as we go. Sam is here, and then he's able to answer those questions as they come in. I'm expecting this webinar to take pretty much the full hour, maybe like 50 minutes plus or minus. So this is what I'm planning on covering. Again, we're focused on the schematic editor. From an analysis standpoint, we're going to go over just how do you create a schematic, how do you set up the topology, what are the different components that are available to you. We're going to talk about operating modes, when it comes to maybe a diplex match, or if you have an antenna in free space or an antenna next to the head. So we'll introduce that concept. And then we'll also talk about subcircuits. This will primarily be discussed whenever we're talking about impedance tuners or aperture tuners and tune codes. But the analysis side is basically just setting up a schematic with your components, your topology, and running that analysis. The next, I guess, set of features that we'll want to talk about is more on the design side. So first of all, you'll be able to specify design goals, like what target metrics are you looking for, whether it's system efficiency or S parameters. So that way you can see as you make changes to your schematic, are you meeting your goals, I guess, with one schematic more than another, or one set of component values more than another. We'll also show you the tuning sliders that are available, where you can just grab a slider, move it back and forth, and you can watch your results update dynamically. And then we've introduced optimization, and so we'll obviously cover that as well. And then a couple other topics has to do with the coupling and the parasitics. I guess if you think about a schematic, probably the first thing that comes to mind is just the schematic layout with the ideal component values. Maybe they're lossy, but you're just using wires and grounds to connect everything. But whenever you go a little bit farther into your design process and it matures a little bit, you'll be taking that matching network and laying it out on a PCB. And so there'll be copper traces and pads, and there'll be coupling between those structures as well as the antenna. And so the ability to capture that coupling and any of those parasitic effects and consider that in your schematic is desirable. And so we'll go over that and show how that can be done. And then also we'll talk about how you can take a schematic and apply it back to your full wave simulation or your FDTD simulation, because there's a demarcation line between what goes on in the schematic and the results that are available in the schematic. Often like S parameters, available power, and that sort of thing. But then there's also all of the full wave results that you're interested in, whether it's far zone radiation patterns or envelope cross correlation or SAR or surface currents, and you want to see all of those full wave results with the schematic applied, and we'll show you how that's accomplished. And so those are the features within the schematic that we're going to want to go over. And then these are going to be the handful of use cases that we touch on. So a simple just fixed band match, just to introduce you the most basic way, into the schematic editor and what it can do. We'll then just build complexity, and so we'll talk about a diplex match. This will allow us to introduce operating modes and optimization and the coupling and parasitics. We'll move on to multiple physical configurations, and in this case, we're going to talk about how do we consider an antenna in free space, as well as an antenna next to a human head, so two different loading configurations, and how do we account for that within the same schematic. Next will be the corporate feed network, and actually those next two are going to go together. So we've got a 1x4 patch array. It's going to have some phase shifters in there and some Wilkinson power dividers, and we'll just look at how we'd analyze that within the schematic, and then also how do we look at those radiation patterns for the different beams that are applied. And then the most complicated example we're saving to the end, and that has to do with a cellular application where there's impedance tuners and aperture tuners, and the need to look at tune codes for the many different states and bands that are supported in that example. So this is, as you can see, at least our use cases here, this is pretty well focused on antenna design, but just be aware that the schematic editor is general purpose, and so we also support MRI design and other applications where a schematic comes into play. So with that, I'm going to go ahead and get started with our first example. In this case, we're looking at a simple L antenna with a ground plane. We're going to put in a matching network, look at a couple of these inductors and capacitors and XFdtd blocks as far as components go. We'll look at design goals and how those are used, and then also the tuning sliders, so that way you can see just how that feature works. And then we'll apply this back to the XFdtd simulation where we can look at realized gain. So let me switch over here and pull up this example. This is the XF user interface. For those of you that are not familiar with it, we have a CAD-based front end where you can manipulate your 3D geometry, assign circuit components, request results, define your materials, etc. And this is the full wave, traditionally the full wave user interface where we run the XFdtd simulations. We've also added a schematics branch down here within the project tree, and this allows you to edit the schematic editor. And so we have an integrated capability within a single product where you can run both the frequency domain schematic editor alongside your full wave simulation and results. And so that just eases a little bit of the workflow in terms of doing this matching network design. So for this example, we have a simple L antenna, across the top. We've got a large ground plane across the bottom. And if I zoom in here, you can see a circuit component just connecting the two. We've run an XFdtd simulation. You got the full wave results. That'll allow us to look at the far zone radiation patterns. It'll also allow us to look at the unmatched S11 results. So here, we're interested in roughly the 830 to 880 megahertz band, shaded in blue. And as you can see, we don't have a very good match like it is. And so we're going to want to build out a schematic to match it. So I'm going to right click on the schematics. I'm going to create a new schematic. I'm going to go ahead and open that. And this is what our schematic editor looks like. It's a window that can be moved around, but we'll just leave it maximized for now. For those of you that are familiar with, like ADS or CUX, those are very broad tools that support a lot of applications, and we've really just kind of like stripped out the features that are needed. So you have your voltage sources, a resistor, you've got lossy inductors, capacitors, switches, phase shifters, an SMP block. So if you're working with a component manufacturer and they're providing you measured component values and performance, you can import those as an SMP file. We've got an XFdtd block, which allows you to bring in the results from your full wave simulation directly into the schematic. There's a couple of voltmeters and amp meters, and then there's a sub-circuit tool and terminal tools, and then a handful of like microstrip based transmission lines that are available to you. So I'm just going to start out by creating a simple matching network just to show you kind of like how this is built out, just a little bit of the usability. So we'll click on a voltage source, go ahead and place this for port 1, place another one over here for port 2. I can select a capacitor, hit the R key on the keyboard just to rotate it. I'll place that capacitor, and then I'll grab one of these inductors, place a couple more of them, rotate it. Now that all my components are here, I can press the wire tool or the W key to go ahead and enable the wires. I can connect all these up. And finally, the G key, and I can place the ground. So there we go. The schematic is built. In this case, we're just like, well, maybe we're going to treat this antenna as an ideal, well-defined, well-designed 50 ohm load. And so does this matching network, provide what we need for a 50 ohm load? We can run the schematic, and it's a schematic editor, or it's a frequency domain circuit solver, so it runs very quickly. We can go to the results tab. These are the results that are available for that simple schematic. And these are pretty much all of the results that are available. Whenever we add an FDTD block, there'll be a couple more results that appear, such as delivered power and system efficiency or radiation efficiency. But these are the standard results you would get from a frequency domain circuit solver. So in this case, we're interested in S parameters. Let's go ahead and right click on this result and add it to our existing graph. We can see that this is the green result is based on the schematic that we have. So this is not quite what we want. And so the first thing that I want to do, or not the first thing, but the next thing that I want to do is add some design goals. So that's one of the concepts that we wanted to cover. And so I'm going to come in here and select my S11 result. I'm going to come into the evaluation. I want to say that S11 is less than -10 dB over my frequency range of 830 to 880 megahertz. And as I can look at my goal report, I can see right now that 0 goals are passed, right? And we already know that based on the S parameter result that we looked at. So what do I want to do, right? I want to change these component values in order to meet my design goals. I can double click on these editors, go in and change the component value, but an easier way of doing that is by selecting the components, opening the analysis workbench, and this opens kind of like a standalone window that brings in the components that I have selected, brings in the result that I had in my graph, and brings in my design goals. So as I move my sliders, I'll see the graph dynamically update, and I'll be able to see whether or not I'm passing the goals that I have specified. One of the things I want to do first is just edit the range of component values. So I can click on this button here. This will open my editor. I can select the capacitor. Instead of it being auto, let me change it to custom, and I want to go from 0.1 to 20 picofarads. And then this also supports multi-select. So in this case, I can select all of my inductors at once, change this from 1 to 20 picohenry or nanohenries, click OK, and now my slider ranges have updated. And so I can go ahead and just grab this capacitance, slide it a little bit to the left, and as I do that, I can see that this other result, the dashed line, is showing me the current state of my sliders compared to the original state. I can grab the next inductance value, start to move this down, and we're getting closer to both the -10 threshold as well as the band I'm interested in. Do one more inductance value. And you can see here that we've, this is the -10 threshold. We've started to be lower than that in a certain aspect of the band, a certain range. And so my goal report has updated, and I'm saying that I'm at 19% of passing the goals that I have specified. So then if I change this last inductance value, there you go, that brings us down below the 10 dB the whole way across, and so we've met 100% of our goals. So that's just how we can use the goals, the sliders for a little bit of manual optimization and tuning. And so before I kind of met what it is I wanted for this, and so before I close this window, there's a couple of things I want to commit. First, I want to take these values, so the new values that I found for the sliders, and I want to push that back to the schematic. And then also, because I changed these component values in the ranges, I want to commit those changes as well. So I just push those two things back to the schematic. I can close it. And now I can see my inductors and capacitors have updated. If I rerun the schematic, I can see that I'm still exceeding 100% of my goals. If I look at my S parameter graph in the project, we can see that I'm getting indeed that match that I found. So that's interesting and all, but this is an ideal, this is an ideal antenna with just a 50 ohm load. So let me go ahead and delete that, because really what I'm interested in is that L antenna that I was analyzing. So I'm going to replace it with this XFdtd block. I can just click on it, drop it in there. I'll use my wire tool to oops, not yet. Let me double click on it to specify the simulation. So this was, the project that I currently have loaded. This was simulation 1 that I ran. So I can click OK. And so now it's, a 1-port simulation with reference to ground. So now I can use my wire tool just to connect that up. If I run this, I can see I'm back to zero goals are passed, just because, the antenna that I actually designed was not a 50 ohm load. I can come into the results and just wanted to point out that we do have system efficiency, radiation efficiency, delivered power. These are some of the new results that are available because we have that XFdtd block and XFdtd simulation available. And I can look at my S parameter graph, and I can see that, yep, indeed, the result moved a little bit on me. And so I want to go back and perform a similar process as before, where I select my components, I open the analysis workbench, I can slide the sliders around a little bit, and wind up with the match that I'm looking for. And again, we're starting to see the success already show up in our bands. And am I going to get to 100? Well, maybe not. Ooh, so close. Oh, there it is. Okay, so we hit 100%, being below our -10. So I can go ahead and save these values back to the schematic. I can close this. And so now I have new component values for the antenna that I simulated, and I'm getting 100% passage of my design goals. The last thing that I want to show here is, now that we have a matching network applied and working, what I want to do is then look at the far zone radiation pattern, right? That's not a result. The far zone radiation pattern is not a result that's typically available through a schematic editor or a frequency domain circuit solver. And so what we need to do is come back to our simulations window, and in the drop down here through post-processing, I can come in and apply that circuit simulation. So when I do that, it'll ask me, like, which schematic am I interested in, which XF simulation am I interested in. We'll go over operating modes in a second, but then I can create this simulation. When I do that, it will add a second simulation to the simulation window, and these results are immediately available, right? There's no full wave simulation that needs to be run, which can take hours or minutes depending on how complicated it is. But this is just a post-processing step where we take the existing full wave results, apply the schematic, and then we can come into our result browser and see that we have 2 simulations that are now available. I can go to the far zone sensor, I can go to realized gain, I can plot both of those. And so now this shows me what is my radiation pattern. In the unmatched case here in blue, this is the original case where there's no matching. And then with the matching network applied, we can see how the realized gain improves with that matching network applied. So this is how you then take that schematic, apply it back to the full wave results, and get to look at other types of output. So that wrapped up the first example. I just introduced you to the schematic editor, showed you how to build out a schematic, how to include the XFdtd block. We went over design goals and tuning sliders, and then how you can apply that back to the XFdtd simulation. You can say those tuning sliders are nice, and then that works on a simple matching network like this, but what do we do whenever things get to be more complicated? And so that's what we're going to cover next. Here we're going to talk about a diplex match. We're going to introduce the concept of operating modes. We're going to show you how optimization fits into this, and then we'll also talk about the coupling and parasitics. So this is going to wind up being 2 projects that I go over with you. The first one being this one. So here in this case, we have just a DILA antenna. If I zoom in, the antenna is just connected to a little stub, and then we have our voltage source or our feed right here connecting the antenna terminal down to ground. As you might expect, we ran an XFdtd simulation, simulation number 1 here, just to get the unmatched results. And once we had that, we then had a schematic that we already designed in terms of the topology. We plugged in the component values and the components and build it all out. And so now we can look at S parameters for this. It's essentially a 2-port network. So we're looking at a 2x2 S parameter matrix. We can look at the reflection coefficients at both port, and we can look at the isolation term or the coupling, the S21 or S12. So if I look at the S parameters here, across the top in blue and green, actually just blue, this is just showing us the unmatched result of what we got before any matching network was applied. The GPS is down here in band 1, or sorry, GPS band L1, around 1.6 gigahertz. And so there's a deep match here within that frequency range, not exactly at the L1 band that's shaded, a little bit off to the side. So we can look at adjusting the component values to get that to match. But then in the Wi-Fi band around 2.4 gigahertz, it's not matched very well. Conversely, if we look at the Wi-Fi port, well, then there's a nice match in the Wi-Fi band, but then not in the GPS port, so that's desirable. And then this yellow graph is showing us S12. So this is just showing us the isolation of the GPS port from the Wi-Fi port. GPS receivers are sensitive, and so we don't want a lot of interference coming from the Wi-Fi port and interacting in with our GPS. So these are the S parameter results that we get whenever we run the simulation for this schematic as it's built. System efficiency is also a result that's available and is of interest. But in order to calculate system efficiency, we can only have 1 port active at a time. So if we're interested in the system efficiency for the GPS port being active, well, then we need to come in and edit our Wi-Fi port, so that way it is essentially treated as a 50 ohm load. We can get system efficiency for that result. We can then, let's see, undo that, and then double click on our GPS port, set this one inactive, and then we can get system efficiency for the Wi-Fi port being active. It should be, pretty much red light. This is an undesirable workflow, right? Like enabling, disabling, running simulations, looking at results. It will give you the results. Let me just show you what that graph looks like. So here, what we're trying to, let me hit the run button so we have actually. Let me do this, hit the run button. And so now we get the results that we're interested in, where the blue graph is the unmatched system efficiency that we got. And then for the green dots here, this is the system efficiency we would get whenever the GPS port is active and the Wi-Fi port's inactive. And then the red one, this is what we would get when the Wi-Fi port is active and the GPS port is inactive. And so the way, I guess, a more user-friendly way of analyzing these 2 different states of being on and off or off and on has to do with the use of operating modes. And so within XF, we have this idea of operating modes. Right now, there's an operating mode for the Wi-Fi mode, a second one for the GPS mode. And if I look at their settings, I can see that for the GPS mode, we have the Wi-Fi port, and it's active set to false. The GPS port is active set to true. Conversely, if we look at the Wi-Fi mode, well, then it's the opposite. And so through operating modes, we have the ability to define both of those states at the same time, which means I can run my results, I can run my circuit solver, I can come into my results tab and I have both the GPS mode and the Wi-Fi mode available at the same time. And so then I have system efficiency available. And so I can grab the system efficiency for both of those modes and plot them and visualize them. So if I wanted to come in here and change this inductance value, well, then I could just change the inductance value, update my results, and get both GPS mode and Wi-Fi mode available at the same time. So that's what operating modes is doing for me, allowing me to analyze multiple states of my schematic all at the same time. We can also tie this in with design goals. And so in this case, we have 3 design goals set up. The first one has to do with system efficiency for the Wi-Fi band, where we're looking at a result that's greater than -3 dB over that Wi-Fi range. Similarly, we have a similar design goal set up for the GPS band, greater than 3 dB over the GPS range. And then we have another goal here, which is based on S12, and we're looking at that isolation being better than -20 dB. And so if I look at my goal report, I can see that my isolation was good. We saw that in the S parameters. The isolation is better than -20, but the system efficiencies were at like -4, -5. They weren't at the -3 target that I was looking for. So, this is where, in the previous example, we can go ahead and select all of these components. We can open the analysis workbench and use those tuning sliders, but this is getting to be a little bit more of a complicated matching network. And those tuning sliders, it just might be too much. And so that's where we'd like to use optimization. So similarly, here we have our table that allows us to select our different inductors and capacitors and specify the range that those values can take on. If you're going to run optimization, you have to say, well, what is the range of component values that each of my components can take on? And so we can do all of that here through this editor, and remembering that there's multi-select available to make this easier to select multiple things at once. And then there's the design goals that we already looked at, and then there is the whoops, wrong button, running of the optimization, which here we're using a particle swarm optimization. I can go ahead and hit the start button. The optimization will start to run, and as it finds a better fitness, well, then those results will get applied back to the schematic. The other way of accessing optimization is to select your component values, open your analysis workbench, and now you have your tuning sliders, where you can manually come in and move them around, and you also have optimization here. And so I can start this optimization. It's going to start. It's going to start, running through the algorithm and analyzing it. It's going to find component values. It might run for a period of seconds or minutes or hours, depending on how complex your schematic is. But you have the ability to stop it and then come over here and edit your tuning sliders. Move these values back and forth, and then come back and re-optimize. And so you have this iterative workflow where you can switch back and forth between starting, stopping, and optimization, and using the tuning sliders. And so what this allows you to do is, like an optimizer, is good, it's useful, but it's not always going to produce the exact result that you're looking for. And you as an engineer have some knowledge on how your matching network applies. And so you can say, yeah, the optimization got me in the ballpark, but I know that my capacitance value here is going to affect my schematic a certain way. And so then you can come in and manually tune these. Yeah, and also there's some trade-offs that can be made where you're like, well, yeah, this is getting me close to where I want on the GPS, but I've got more leeway on my Wi-Fi, and so I can adjust these accordingly as well. So just knowing that you have an iterative workflow here of switching between optimization and tuning sliders in order to find a place where you finally matched all of your design goals is a feature that we allow, or that's available within XF. So then the last aspect of this project that I wanted to show had to do with the coupling and the parasitics. So here you found, let's just assume that we had 100% passing on our design goals, and we then wanted to move out of this ideal schematic environment where we're using wires and grounds to connect everything, and we're going to move to our PCB board, where we've come in and laid out the actual matching network. So in this case, we have our GPS port over here on the right-hand side connected to ground. We've got our Wi-Fi port across the bottom, and then we have all of the other inductors and capacitors comprising the matching network laid out here. And so now that we have this full 3D structure, we have the copper traces, we have vias, we have pads, we have antenna coupling onto here. And so this is going to require us to come up with new component values, because the old component values from the ideal schematic are not going to work here due to that coupling and matching network parasitics. And so in order to analyze this, we come into our simulations window. In this case, there's a response matrix simulation that we'll create. As I can see that there are 10 ports over here in my circuit component list. And so this response matrix is essentially going to create a 10 port, 10 by 10 matrix that has all of the matching network parasitics accounted for and captured. So once I have that response matrix, I can come into my schematic layout, and this might take a minute for you to adjust to this new type of layout or way of thinking about it. But I have my 10 port response matrix simulation here, and then on each one of those ports I have the capacitor value or inductor value or the voltage source applied here. And so it's essentially it doesn't look like the layout that we saw in the previous example where you have your, the layout like you had over here, right? It doesn't look like this, but we've taken the 3D structure, put it into here, and so now we're just interacting with the individual components. And so whenever we change the inductance value or the capacitance value, we're considering the matching network parasitics and all of the full wave effects in our results. And so the same idea of having design goals, allowable component values, looking at S parameter isolation or system efficiency results, having tuning sliders, and optimization, all of that is, all of those features are still available in this type of setup. It just so happens in this case we're analyzing this full geometry whenever we're deciding on our component values. So that's the Diplex Match example. We introduced operating modes, optimization, and the coupling and parasitics. So the next example that I wanted to look at here has to do with multiple physical configurations. So we're going to have an antenna in free space. We're going to have an antenna next to the head, so 2 different loading configurations. And there's going to be essentially a 3-port switch here that determines whether or not we're using a larger inductor value or a smaller inductor value. And again, operating modes are going to come into play. So if I pull up this example, here we have the phone, in free space, the phone next to the head. And when I created my full wave simulation, there's 2 of them. So in the first simulation, we went into the meshing properties on the head, removed the meshing for it. So that way it was only the phone that was included in the simulation. And then for simulation number 2, we enabled the meshing properties for the head. The simulation got a little bit bigger, used a little bit more RAM, but we got the results for the second loading condition. Once we have those 2 simulations, we created a schematic. And this is similar to what we saw in the slideshow where there's the inductor shunt to ground. We had the option between a higher inductance value or a lower inductance value. We had our 3-port switch, and if I double click on this, we can see that there are essentially two files that are imported. So what is the fit switches performance if it's off on versus on off. So I have those two different states that are loaded here. And then similarly, if I double click on the XFdtd simulation, I've got simulation number 1, which is the phone in free space, and then simulation number 2, which is the phone against the head. And so these two XFdtd simulations are also included. And I've used operating modes here to define my two different states. So, in the free space state, we're using the on-off switch configuration, and we're using, free space simulation number 1. And for the against the head state, we're using the opposite switch, so off on and simulation number 2. So if I run this and come in and look at the results, I've got my two operating modes, both against the head and free space. I can grab S parameters, I can plot that result. And now I can see, across the top, these were my unmatched results from my first two simulations. Poor performance, but then down here I can analyze what is my matching network, or what is my performance with S11 for the two different, the free space as well as the against the head. So if I were to, have design goals, if I were to use the manual tuning sliders, if I were to run optimization, to change those inductance values, well, then I would be seeing these values, both of these values update together at once. That's just a usability workflow that allows you to analyze multiple states of your schematic all at once. But that was just a quick example, basically showing you how we can bring in multiple XFdtd simulations into your schematic and use operating modes to analyze them. The next example here, this is going to look at the corporate feed network for the antenna array. In this case, we've got some phase shifters, some Wilkinson power dividers, and we can see, again, we're using operating modes to define multiple beam states. And then when we apply the schematic back to the XFdtd simulation, we can look at the radiation patterns and see how they change based on the phases that are applied at the phase shifter. So for this example, we talked about the 4-element patch array. We had 4 circuit components that are defined for each. We ran an XFdtd simulation, which gave us that 4x4 S parameter matrix. We had a far zone radiation pattern available, a full 3D pattern. And then we could come into our schematic and I'll zoom in first. So this is the XFdtd block, the XFdtd simulation that brought in that 4x4 S parameter matrix. We then went and hooked up 4 different phase shifters to each. And then we put in a series of Wilkinson power dividers, which is our corporate feed network, and that brought it all back to our voltage source, port 1. We have operating modes defined here. So we have 4 different beam states. And if I look at them, beam state number 1 is using a 0-degree phase shift across each. Beam state number 2 is applying a 30-degree delta between them. Beam state 3 has a 60-degree delta, and beam state 4 has a 90-degree delta between them. So I can, solve this circuit. I can graph the results, and if I'm looking at the reflection coefficient here at port 1, I can see how that reflection coefficient moves around depending on which beam state that I'm looking at. And if I, move out of the schematic and come back to my simulations window, I can, again, come in and post-process, apply a circuit simulation. Again, there's one schematic, one simulation, but then I can select my 4 beam states. That will allow me to create a second simulation window, a second simulation here in the window. Again, these results are instantly available, and so I can come into my result browser. I can scroll down and find essentially my 4 3D radiation patterns and grab the gain for each and view them. And so this allows me to view the results one at a time. So these are the different beam states that I have selected, or I can view them all at once. But basically, again, just another example of how we are able to take a 4x4 S parameter matrix, apply phase shifters to them with different operating modes, and then apply the schematic result back to the XFdtd simulation, where we can then look at the far zone radiation patterns for them. All right, 20 minutes left. And we're on to our last example. This is the most complicated example. And in this case, we are going to, well, I guess the newest feature, the feature that we haven't covered yet, is going to be subcircuits. Where we are representing an impedance tuner as well as an aperture tuner within our subcircuits, and then using them with the rest of the schematic. In this case, we're going to jump straight to the layout on the PCB board to cover the parasitics and the coupling. And so let me go ahead and open this project. Here is our antenna. You can see that there's a port here on the impedance side where you would put in your matching network and your port. And then over here, this is on the aperture side, and I'm going to start over here just because it's simpler. And I'll just cover, hopefully briefly, just an introduction into tuners. So in this case, we're using an aperture tuner, which is essentially a switch where we have the RF feed coming into the antenna, and this red box is just a cuboid with the faces set invisible, and we drew red lines for the edges. So that's all that we're visually rendering here, but it's supposed to represent the chip. And so the chip has 3 pins. There's the RF connection to the antenna, and then this there's a switch in here, which either we switch between the left side or the right side. And then that allows us to grab a component value. So this would be one of the loads that we're switching in or out, and then this would be the other load that we're switching in or out. And depending on what these switch state is within the aperture tuner, as well as the load values, we're essentially changing the input impedance of the antenna that we would see from this port, right? So if we're looking at the input impedance from this port over here looking into the antenna, that input impedance is going to change depending on the switch states and the loads that are seen over here. And so if you think about smartphones these days, they've got many bands that need to be supported, and instead of making this antenna longer or shorter, which we can't do once the phone's manufactured, we can use a software controlled capability to change its input impedance. On the input side of things, we have a much larger impedance tuner. Again, this is just represented in blue, so you can see which terminals are inside the impedance tuner and then which ones are outside. There's multiple ports here that are outside the impedance tuner that are allowing us to switch different values in and out. The impedance tuner itself has 5 switches within it, as well as 2 capacitor banks. And so in total, there's 25 ports here within the full wave simulation. We created a response matrix, ran the simulation, got the 25 port matrix, and then we were able to bring that into the schematic and build this all out. So this is the 25 port XFdtd simulation that we have. Some of those ports are connected to the fixed component values, those inductors or capacitors that are outside of the tuners. And then we have the tuners represented. This would be the impedance tuner, this would be the aperture tuner. And in order to just introduce subcircuits and talk about this in a little bit more detail, I have a different schematic here where we're just going to talk about the tuners themselves. So looking at our impedance tuner, we can see that, yep, there are 5 switches as we go around, and then there's 2 capacitor banks that are available. this text up here is just showing us what are the states of all of those values, and I can double click on this, and this will open up the editor. So we have the two capacitor banks with all of those values available. We have the switches, which are essentially on or off. And then depending on the state or the values of the switches and the capacitors, we'll have these registers as well as the tune code. So if I, right now the tune code is 1111.0. If I switch this from on to off, well then the tune code dynamically updates as well as the register dynamically updated. If I had a tune code like that the colleague provided, and they said, hey, plug in a new tune code, well then you can just copy and paste that tune code into here, and your switches and capacitors will update accordingly. I can, if I wanted to right click on this schematic, I could enter it, and I could go into the subcircuit, and I could see, how all the different terminals are laid out, and the different SMP blocks that were imported. We don't need to do that. Just be aware that you can obviously enter and exit your subcircuit and actually see the contents of it. But from a consumer, from the parent level schematic, this is primarily what you're interested in, right? What are the values of each of the components that are in my schematic? And you'll notice here that we have a nice symbol. It's representative, so that way you can see, oh, all right, well, this terminal goes with switch 4, this terminal goes with ground. And this is a custom symbol that has been entered. If I just move over here to the left, we can see that this would be the default symbol. So this is just showing you what are the names of all of the terminals, but there's no graphical representation. And so with our subcircuits, and really all of our circuits, you can right click on it, you can come into the symbol, and you can edit the custom symbol. And so this allows you to bring in the image as well as define text and produce something that's more user-friendly. So this is what we have for the impedance tuner, and then something similar for the aperture tuner. And this might make a little bit more sense now that you're seeing it. This would be the terminal that went to the antenna, and this would be a terminal that goes to one of the loads, and then the second load. And so here, this is just what the schematic looks like with all of that applied. There are, the ability, as I showed in all the previous examples, we can define our design goals. We can use tuning sliders. We can use optimization. We can use operating modes to analyze the many different states. In this case, we do have operating modes set up. There's 4 of them, and these are essentially just defining what is the tune code for the impedance tuner, what is the tune code for the aperture tuner, and therefore then what are the associated switch states and component or capacitor values that go with it. And if we look at the S parameter results, well, these are the S parameters that we get across the different bands that we are interested in. And also, through the schematic, we have system efficiency. And so these are the system efficiency results that we get across the bands that we're interested in. So that pretty much wraps up the examples that I wanted to show. And just again, in summary, we looked at how the schematic is defined with all the different components, operating modes, subcircuits, and then you go about designing it using design goals, tuning sliders, and optimization. We can also account for the matching network parasitics, and we can apply that schematic back to the full wave results. And these are the different use cases that we took a look at today. So right on the dot, 50 minutes. So we have 10 more minutes here. Again, well, not again, but we did record this session, and the recording will be sent out later today. So you can look for that in your email, maybe check your spam folder if it doesn't show up, or if you don't see it in your inbox. And now we've got a few minutes for questions. I'm going to pause and see if anything came in while I was presenting. Oh, we did have a handful of questions. Let me see how complicated they are and see if I can answer them here on the fly. Okay, so there was a question here asking about can you assign relative weights to the optimization goals? And the answer is yes. Yes, you can. Let me, which example was I looking at? There was let's look at this one. Let me get this question bar out of my way again. Okay, so here we're looking again at the Diplex Match. We had our design goals specified here. And if I just select one of the goals and come under the evaluation tab, there's a weight right here. So this is allowing you to set different weights. I guess I need to leave this larger so you can see them all for the different goals. So if we wanted to say, hey, system efficiency is a higher priority weight, we can do, system efficiency for Wi-Fi is set to 2, GPS is set to 2, and the isolation we can leave at 1. So if you look at that over here, this is the weight. These are both set to 2, and this is set equal to 1. So yeah, we have weighting capabilities for the different goals. If you want to get more advanced, you can weight it differently. So do you want it edge weighted, center weighted, peak and average? So that even gets into another level of, I guess, advanced settings. But yes, we do have the ability to weight our goals. All right, so there was another question about whether or not we provide tuner models from major manufacturers such as Qualcomm. Remcom does not distribute those models directly, but Remcom has been in touch with some of the manufacturers. They're aware of our subcircuit capability. They've created some example subcircuits, and so the process there would be, you as an end user would want to get in touch with, Remcom and or your supplier and put in a request. Typically the request for creating these models needs to come from you, the end user, and then Remcom and your supplier can work together to make sure we're getting you the model that you need. But then the model would come from your supplier. So there's just a little bit of coordination there that needs to happen, but yes, we can make those available to you if you can put in a request for it. All right, there was, well, let me just check. Oh, still a couple more minutes. Okay. So there's another question here. Does XF include the 3D CAD model of the CTIA SAM Phantom? The CTIA CAD models is distributed by that organization. That's not distributed by Remcom. As members to the CTIA organization, like, you'll have access to those files that you can download, and the SAM Phantom would be one of those models that you can get from them. So again, Remcom's not distributing those CAD models because we don't own them, but you can get them if you're a member of the CTIA organization. All right, there's another question here on the 4-patch example. What does the R component between the array feed lines mean? Let me take a look and see if I can pull that example up. So the 4-patch example, if we look at our schematic, we have the R component here. And so this R component, I guess I did not design this example, so I don't know exactly, but I would say that this, we're using Wilkinson power dividers, and whenever I've seen that used in the past, there's a resistance value across there. But I cannot, I don't know the design decisions for why that is, but we can, obviously I know the engineer that created this example, and I can follow up with him and get back to you on that. Okay. Another question here, it says, in the tuner optimization, is it possible to optimize concurrently the tune codes and the loading components? So I think what this means is, let me pull up this example and let me go to the geometry and say, so the question is that, we have the, what I'll call the, well, we have the impedance tuner, where there's a tune code that controls the switch states and the capacitor values within the impedance tuner itself. And then separately, there are the fixed components outside of the impedance tuner. And these fixed components, you need to determine those values as well. And so the question is whether or not we can optimize that concurrently, and the answer is yes. Here within the schematic, this is that 25 port XFdtd simulation that we ran. These are those fixed component values, or those fixed components. And then these are the aperture tuners. And this example is not fully fleshed out and set up for it, but yes, you have the ability to specify design goals for the different operating modes, specify the allowable component ranges, for these fixed components, and then your optimization will consider all of that at once when it's determining the tune codes as well as the fixed component values. So yes, we can concurrently optimize that example. All right, just based on time, since we have 2 minutes left, I'm going to go ahead and hold off from answering the rest of the questions. We can follow up afterwards as needed, but want to say thank you to everybody that attended. Thank you very much for your questions. I hope that this was informative and gave you, I guess, a comprehensive view of what is possible. Now that the 7.11 release is out, we've added optimization, system efficiency, and subcircuits, and incorporated that with all of the existing schematic editor functionality with the tuning sliders, the design goals, and that sort of thing. So if you have any questions, certainly feel free to reach out to us. There's our phone number as well as emails, and where you can find us on the support site, or sorry, the World Wide Web. And we look forward to talking to you about this further. I hope you enjoy the rest of your day, and thank you for your time and attention. Bye.